Lesson 8.6, page 460, comparing linear, exponential, and quadratic functions. In this lesson, you will learn how to choose functions to model data, how to choose which function would model the data, how to compare functions using average rates of change, and how to solve real-life problems involving different function types. Choosing functions to model data. So far, you've studied linear functions, exponential functions, and quadratic functions. You can now use these functions to model data. We learned about linear functions in Chapter 4 and 5, exponential in Chapter 6, and quadratics in Chapter 7, and also what we've covered in 8. We are going to review a little bit of each of these today. Linear functions. Remember, linear means straight line graph. Linear functions can always be written in slope-intercept form. Remember, y equals mx plus b. Exponential functions. Those functions are the ones, remember, we have the Grace Groner story where she started with 3 shares of stock worth $180 and made $7 million. Those functions can be written as y equals a times b to the x power. They start near 0 and explode upward. That would be exponential growth, or remember we could have this look where they start high and finish low. That's exponential decay. That is what we learned in Chapter 6. And then the final form of function that we know so far is called a quadratic. Those are the parabolas. And this is standard form for those functions. We've learned that in this chapter. We need to be able to look at a graph and determine what type of function we have. So they will have you do this in the bookwork. They will have you plot points and determine what type of function you have. We'll do one quickly together, like an A. The point 4, 4, 4 right, 4 up would be here. 2 right, 0 up, 0, 0, 1 right, half down, and 2 left, 4 up. You notice how I'm getting a parabola. This has to be a quadratic then. And then they show you a sample of B and C where we have points lining in a straight line. That means we have a linear function. And these points plot and create exponential growth. It should be easy for you to plot points and tell me what type of function you have. I think just to shorten up the video, I think that's an easy concept, so I'll skip this. Instead of having you do this, I think you can plot points and tell me what type of function you have. You'll definitely practice that in the homework anyway. We are going to need to be able to look at a table and write a rule, which means write an equation for that table. That's what this portion is going to show us how to do. You can use patterns between consecutive data pairs to determine which type of function models the data. The differences of consecutive y values are called the first differences. The differences of consecutive first difference are called second differences. That second or that blue sentence probably doesn't make sense. I'm going to put a little star next to this. We're going to talk about this more in a minute, so don't worry about it if it's not making sense right now. Now we're going to review each of these. Linear, we've already learned how to look at a table and determine if it's linear. The first differences are constant. In other words, we have a constant addition or subtraction pattern for x and y. If that happens, we have a linear table. You've already actually looked at tables and found out if they were linear in Chapter 5 and 4, and I also made you do it again in Chapter 6. We also learned about exponential tables. If the y values have a common ratio, it's an exponential table. Another way of saying that is if we have a constant multiplication for y, you have an exponential table. Now a quadratic table happens when the second differences are the same. So let me highlight there. Second differences are the same if we have a quadratic table. Now you notice here is that second difference vocabulary again. All right, so we'll talk about second differences in a minute when we see a quadratic table. In all cases, the x values have to have a constant pattern. So in other words, if you look at these tables, you notice how x is always increasing by 1, for example. in all three patterns, the x values have to have a constant addition pattern to them. All right? Okay, so let's actually take that previous slide, and if you're like, I'm not really sure what you're talking about, let's talk about the previous slide. We are going to use the previous slide to figure out, are each of these three tables linear, exponential, or quadratic? Now, there's a little tip here. They say first determine that the differences of the consecutive x values are constant, then check whether the first differences are constant or consecutive y values have a consecutive ratio, common ratio. If neither of these are true, check whether the second differences are constant. That doesn't sound easy, okay? It is easy. This is all this is telling you. It's just saying check if the table's linear first. If it's not linear, then see if it's exponential. If it's not exponential, check if it's quadratic. So let's go to the first table, okay? Let's see if it's linear. X goes up 1 every time, okay? Y, take away 3, take away 3. Oh, this is definitely a linear table. We have a constant subtraction pattern as we add 1 for x each time. So the first table's linear. That was easy. Let's go to the second table. Okay, let's see, is it linear? X goes up 1 every time. We're good there. 1 plus 1 is 2. 2 plus 1. Oop, it's not linear. Let's see if it's exponential. Exponential is a multiplication pattern. 1 times 2 is 2. 2 times 2 is 4. 4 times 2 is 8. This is definitely an exponential table. It's a multiplication pattern. Let's go to the third table. Let's check. Let me erase this so we can see it better. Is it linear? Well, let's check. Plus 1, plus 1, okay? Let's go down here. Negative 1 minus 1 is negative 2. Negative 2 minus 1, negative 2 minus 1 is not negative 1. This is not linear. Let's see if it's exponential then. Negative 1 times 2 is negative 2. Is negative 2 times 2 negative 1? Nope. It's not exponential. So here is where that second difference thing comes into play. And I haven't explained what it is. Okay, let's figure out the second difference. It's easy to do. Remember, difference means subtraction. So let's get the first difference. So in other words, you're going to subtract each of these. Let's do that. I'll put little triangles. I'm going to subtract each of these. Ready? Negative 1 minus negative 2 is positive 1. Negative 2 minus negative 1 is negative 1. Negative 1 minus 2 is negative 3. And 2 minus 7 is negative 5. Those are the first differences. Okay? This says if the second differences are the same, it's a quadratic. Okay? The first differences I have. Now I got to figure out the second difference. So I got to do another set of subtraction with these numbers. Now, if all these work out the same, then I know I have a quadratic. Let's check. 1 minus negative 1 is 2. Negative 1 minus negative 3 is 2. Negative 3 minus negative 5 is 2. The second differences are all the same. So I have this table has to be a quadratic table. I want you to pause the video and you try to find what type of table this is, and then I want you to write a rule for the table, okay, or write a function for the table. And we're back, okay, so first of all, this table is definitely an exponential table because do you notice we're timesing by 3, times by 3, times by 3 as we add 1 every time, okay? I guess I said find a rule. We'll practice finding the rule in a minute. I'll get back to this. But anyway, this is definitely an exponential table. Okay? They don't ask us to find a rule, but we'll talk about that in a minute. It's definitely an exponential table. Okay, I got ahead of myself. Here's where we're going to talk about how we write a rule for a table, how we write a function for the table. So we're going to have to be able to write a function for a linear table, an exponential table, and a quadratic table. So we need to review each of those. Okay, so let's talk linear. Let's go back to our previous example, this was a linear table. Okay? Remember, linear is slope-intercept form. So let's think about this. Remember how we were subtracting 3 every time? Just talked about this a couple minutes ago as we add 1. So we were going down 3 as we ran 1. Down 3, run 1, down 3, run 1. The slope of that table is -3. So I'm going to put a -3 in for m. Now, I need the y-intercept. Look at the table. Do you see how the y-intercept, I'm highlighting it, is 2? That means b is 2. So plug a 2 in for b. There is your equation for that table. That's a linear table. Y equals -3x plus 2 would be the equation for that table. Okay, let's review exponential. How do I write a rule for an exponential table? Now remember, this table we were multiplying by 2 every time. Here's how you write the rule. Remember, exponential functions have that equation form. So let's review this. B is what you multiply each time. I'm multiplying by 2 each time. So put 2 in for B. A is your y-intercept for an exponential equation. So let me highlight the y-intercept. It's right there. Oh, I was wanting to highlight it. I'll circle it. It's right there. It's 4. A is 4. Okay, there's my rule or my equation for that table. Y equals 4 times 2 to the x power would be the equation for that table. For this one, this was exponential, so I know it's the same form. Y equals a times b to the x power. I'm multiplying by 3 every time, so b is 3. There's my y-intercept, 3. There would be the equation for that table. So I reviewed linear and exponential, how to write an equation for those tables here on this slide. Now we have to figure out how do we write a rule or an equation for a quadratic table. Now, one thing I have an issue with in the book, they're showing us how to do it on paper, which is great, but here's the issue. You can only use this technique if you know both x-intercepts of the table, and sometimes the table doesn't give me both x-intercepts. So I'm going to show you how you can get this on your calculator. So take out your calculator, and we're going to take this table, and we're going to type that table in our calculator first. So we're going to review doing that. So to type a table in your calculator, you're going to go to the Stat key, hit Stat, Edit, and I want you to type that table in your calculator. I already have it typed in here just so I can speed up my video. So pause the video, type the table in. After you have the table typed in, go back to Stat again. So hit Stat, arrow right to Calc, and if you go down to option 5, we already know the table's a quadratic. We want to do a quadratic regression. So if you go to option 5 and press Enter, on the new calculators you might have to scroll down to Calculate and press Enter again. You should see this information on the screen of your calculator. And here's what this is telling you. There's standard form. A is 1, B -12, C 32. So you notice I wrote the equation for that table. I just kind of underlined it there. My pen's kind of stopped, and there we go. Okay. So as I look at the book now, I'll see, oops, went the wrong way. I will see there's what the book has for that. So I was able to use my calculator, plug the table in, do a quadratic regression, and I will get the equation for that table done. Why don't you try real quick, take this table, pause the video. I want to know if this table is linear, exponential, quadratic, and then I want you to write a rule for the table. And I'm back. I hope you figured out the table's exponential and that the rule would be y equals 8 times half raised to the x power. If you're not sure about that, make sure you ask in class. Okay, so next we're going to compare functions using average rates of change. For nonlinear functions, the rate of change is not constant. In other words, we can't just, remember, a table where we're adding the same thing every time is linear. On nonlinear functions, the rate of change isn't the same. However, you can still compare nonlinear functions using the average rate of change. Now, when you look at this, it's going to be like, what the heck is that symbolism? That symbolism is really telling you just use the slope formula. Do you remember the slope formula from Chapter 4? If you use this formula, you can calculate the average rate of change on curved graphs. Just use this formula on an exponential or quadratic function. We'll practice this here in a minute. There'll be good review of stuff we learned in first semester. Now this next part, I'm not even going to read this. I highlighted it. It's wordy, and when you read it, it can sound super confusing, but it's trying to tell you something really easy. And here's what it's trying to say. I put it in my own words here, and like, what is this? Okay, here's in my own words what these two things are trying to tell you. Suppose you have a linear function, an exponential function, and a quadratic function, and they all have the same rate of change. So you use the slope formula, you calculate the slope of each of these three functions, and you find out they're all exactly the same. What the pink and green writing is telling you is this. The exponential function, if we had a three-way tie, will end up growing the fastest. The quadratic function will grow second fastest, and the linear would be in third place if all the rate of change were exactly the same. Okay, let's practice figuring out the rate of change, and here's a sample problem. 2 social media websites open their membership to the public. Compare the websites by calculating and interpreting the average rates of change from day 10 to day 20. So let's do that first. Let's go to website A. Here's day 10, here's day 20. So I'm going to write those 2 points down, 10, 1400, and 20, 2150. Look at, they're using the slope formula. Can you see that? They took the y values and subtracted on top. They took the x values and subtracted on the bottom. The rate of change for website A is 75 members a day. Now let's go to website B. Okay, this point looks to be the point 0 and, timeout, I misspoke here. I need day 10 and day 20. This point, day 10, looks to be the point 10, maybe 850. And on day 20, it looks like we have about day 20 is 1800. Okay? They took those 2 points, and they are finding the slope. They subtracted the y values, and then underneath subtracted the x values. The rate of change on website B is 95 users a day. Do you notice how the rate of change is higher for website B? So if we go from day 10 to day 20, we would predict that website B would have more users after 50 days. Okay? What I'd like you to do real quick is you try to compare these 2 websites from day 0 to day 10 and tell me which one do you think would have more users after 50 days based on those rates of change. Okay, and I'm back. For website A, let me get my highlighter out. Here's day 0 and here's day 10. So I took those 2 points. The 2 points were 0, 650, and 10, 1400. And I took those 2 points and I put it in the slope formula, and I figured out that website A had a rate of change of 75 members a day. Let's go to website B. I took the points on day 0, 590, and day 10 looked like 890. I took those 2 points, I put those in the slope formula, and I found the rate of change for website B was 30 a day. Okay? So right now, based on that, it looks like website A is growing at a faster rate than website B. To wrap the video up, we can compare different types of functions using our calculator, and this is a review again, and using the intersect feature on our calculator. We learned about this feature back, I believe, in Chapter 7. I'm pretty sure it was Chapter 7. Might have been Chapter 6 we used this feature. We'll review it today. Okay? In Littleton, 1900, they had a population of 1,000 people. Littleton's population increased by 50 people each year. So if they're increasing by 50 people a year, that's a constant rate of change. That means Littleton would be a linear equation. So 1,000 is what they started with, and they're increasing by 50 a year. There's the rate of change. So can you see a linear equation for Littleton? Now, Tinyville had a population of 500 people, and their population increased by 5% a year. If you're growing 5% a year, that's exponential. So remember, we had a growth formula for exponential. This is back from chapter 6 for sure. There was a growth formula. So the initial amount was 500. 5% would be 0.05. We'd plug that in here. So 500 times 1.05 raised to the x power would be the equation for Tinyville. We want to know when the populations were equal. So this is where we would use the intersect feature on our calculator. So let's go back to our calculator. Let's type those two equations in the calculator, which you see I just did. Now, before we go on, we need to see where these two graphs meet, and that would be the answer to the problem. Now, I know the answer has to be positive because we're going forward in time. We can't go backward in time. So I need my graph to be positive. Now, your graph is normally set like this, where we have all four quadrants. And right now, we don't need all four quadrants. We only need this quadrant. We need the first quadrant. So I'm going to set my calculator so that's only in first quadrant. And I'm going to pick pretty big numbers because we do have pretty big numbers here, okay? So I think what I'm going to do is I'm going to set my calculator that my x domain will go from, let's say, 0. I'm going to go from 0 to 100. And my y domain will go from 0 to, I'm going to put 10,000 because these towns, I don't know how many years it's going to take. We're having 1,000 in one town, 500 in the other. So I'm going to set my window to go from 0 to 100 for x, 0 to 10,000 for y. So let's do that. So to do that, go to window. Our x, we want to go from 0 to 100. There's my domain for x. And for y, I'm going to go from 0 to 1,000. So if you're not understanding what I'm doing, this is all I'm doing right now. When I graph this on my calculator, this is what's going on. I'm going to go from 0 to 100 on my x-axis, but from 0 to 10,000 for my y-axis. Okay, so let me graph. We're making a graph. Let's see if these two graphs meet. Trying to find it. Oops, I don't see anything in my picture. Oh, and I see I made a mistake. I didn't get 10,000 here. I only got 1,000. So let's go to 10,000. I got to put another 0. Now let me try it again. 110,000. Let's try graphing that again. Okay, now here we go. You can see in this picture now, you can see that these 2 points meet. So let's use the intersect feature to find out where they meet. So remember, we're going to do second, calc, option 5, and press enter 3 times. Okay, so according to this, in a little bit more than 34 years, the two towns will have the same population. So when you look at the information in the book, got to go back, this started in 1900, so it's in about the year 1934 or 1935 when these two towns would have had the same population. I'm going to stop the video here. If you have questions, make sure you ask in class.